Right, that's where we were up to. 3 reprocessing plants built at Sellafield, and by the end of this year, all 3 will have closed. I emphasise possibly only one's being decommissioned, but not fully decommissioned, and the other 2 will be, once Magnox closes at the end of this year, will be placed into POCO, post-operational clean-out.
Harry, can I ask, sorry, what was the first reprocessing plant other than Thorpe and Magnox Repro? What was the one that has been decommissioned?
It'll be building 204. And it may have only been partly decommissioned. Magnox was 205, and obviously Thorpe was the third standalone.
70.
But 204 was, in terms of capacity, was a very small amount, and in terms of uranium throughput, and in fact was used for non-civil purposes. Okay?
Thank you. Thank you.
Is that okay?
Yeah, that's super. Cheers.
So reprocessing, it provides this closed nuclear fuel cycle, and in reprocessing we rely on this process called solvent extraction, which we discussed on a Monday. And solvent extraction is about separating the uranium and plutonium, separating them individually, away from actinides and fission products. Okay, that's the whole essence of reprocessing. So, okay, but before we start discussing reprocessing, the obvious question is, well, why do we reprocess? And people believe that we actually take fuel out of a nuclear reactor to reprocess. As the next 2 or 3 overheads will demonstrate, we don't. We have to take the fuel out of the reactor because the fuel is undergoing certain changes, and those changes ultimately affect its performance. And as you remember, in a reactor, we're bombarding essentially, primarily at the start, uranium-235 with neutrons. That particular isotope undergoes fission, produces more neutrons, produces fission products, and obviously what we're looking for is a large amount of heat. During the reactor continuing with the fission process and the chain reaction, what subsequent happens is the uranium-238, and bear in mind the bulk of the uranium is in that particular isotope, it captures neutrons and subsequently is converted into plutonium. Some of those plutonium isotopes are also fissile isotopes, okay? So that's what's happening inside very diagrammatically. But as I've just said, there are in-reactor changes. The actual fuel inside the fuel bin, whether it be stainless steel or zircaloy, we have physical and compositional changes due to the neutron irradiation. The fissile material content, 235 initially, and subsequently 239 and 241, decreases progressively by fission. And not surprisingly, when we take the fuel out of the reactor, there's significantly less 235 than the original fuel composition. In addition to the fissile material, we've got accumulation of new elements in the fuel itself. Bear in mind, for AGR and light water reactor fuel, we're talking about an oxide pellet. For Magnox, we're talking about a uranium metal rod, right? And as a result of the accumulation of these new elements, as it indicates there, transuranic elements, neptunium, americium and curium, and fission products, strontium, cesium, technetium and many more, some of which are neutron poisons, such as gadolinium. And it's these changes plus the formation of these fission products and other actinides why we take the fuel out of the reactor after a certain length of time. And these changes result in actual swelling of the actual pellet, because the material that is being produced is, in terms of volumetric, is larger than the material it is replacing. So the actual fuel actually swells. In addition, there's some of these fission products that are created, the gaseous fission products, and we make an allowance, as you will have probably heard or will hear, we make an allowance for these gaseous fission products in how we construct or how we design the fuel assembly. But these gaseous fission products, some of them have very little solubility in uranium, and therefore we have to accommodate them within the pin geometry itself. All of these changes affect the physical and structure of the fuel, whether it's modifications to thermal, mechanical or dimensional changes. And as a result, the cladding deteriorates or can deteriorate, which result in the formation of cracks. And we have known even the fuel component, the actual stainless steel and the zircaloy, actually breaks and breaks open. And that obviously is a major challenge for the reactor people. Now, when you're told about the actual fuel and particularly the fuel pins, the actual stainless steel and zircaloy, the actual thickness of that material is probably no more so than the Coca-Cola can you can now buy. And you can, if you remember, you can simply squeeze a Coca-Cola can with very little pressure. And the fuel pin thickness, the stainless steel and the zircaloy, is something resembling the thickness of that Coca-Cola can. It has to be, because if it was thicker, it would probably prevent the neutrons or slow the neutrons down, and equally it would absorb a significant amount of heat, which we don't want, of course. So finally, what happens in the reactor is it's indicating that particular illustration shows you what happens if and when we leave the fuel in the reactor. Then that's showing a cladding breaking of and fracturing of the cladding. And it's summarizing there the actual changes in the reactor: decrease of the content of fissile material, progressive poisoning of the fuel, risk of cladding break. There we're demonstrating we have cladding break. And before all of this happens, the actual fuel is removed from the reactor. And it's removed long before all of the fissile material has been consumed. So the actual reason for removing fuel from a nuclear reactor has really nothing to do with reprocessing. It's all to do with reactor performance and the changes in the fuel that's taking place inside the reactor. I should have mentioned, and apologies, ladies and gentlemen, with this particular presentation, and I think possibly the next two that I'm scheduled to do, there is an extensive note page to these overhead presentations, and there's a good deal of explanation and comments in those note pages and I would strongly recommend you actually read those note pages in addition to looking at the PowerPoint presentation. Okay? So why do we reprocess? Well, we've taken the fuel out of the reactor. Why do we reprocess? And jumping slightly ahead of my presentation, we do not have to reprocess. But in the United Kingdom, we decided we would do so. And one of the reasons for that decision was to recover fissile material 235, 239, 241, for example, to use it in for the fabrication these days of new fuels such as MOX fuel. But when the United Kingdom decided we would reprocess, we didn't talk about MOX fuel. MOX fuel hadn't entered into our vocabulary. But what had was a fast reactor program. We had a very intensive fast reactor program at Dounreay. And I think we built something like 3 to 5 fast reactors. But unfortunately, a decision was made that we wouldn't pursue fast reactor technology. And as a consequence, it then presents the reprocessors with a little bit of a dilemma. And the question will be asked, well, why are we reprocessing? We can't use the plutonium. And bear in mind, I'm talking about pre-MOX. We can't use the plutonium because we no longer have a fast reactor program. So that created some challenges. The usage of plutonium in MOX fuel, we probably certainly generate far more plutonium than we could use in MOX fuel. Certainly in the United Kingdom, that's the case. Because the AGR reactors, it was decided many years ago by the previous owner of the AGRs, the Central Electricity Generating Board, that MOX fuel would not be inserted into AGR reactors. So that left the United Kingdom with only one reactor at the moment that possibly could take MOX fuel, and the United Kingdom has not shown a great deal of interest in using its reactors for MOX fuel. So therefore the reprocessing debate started to become more focused. The reason for reprocessing, or the second reason, was separation of nuclear waste, the activation and fission products, separate those away so we have a much smaller quantity of waste to handle, and possibly handle it in a more sensible manner. But I'll skip slightly ahead, but I'll not show the overhead. All of the debate about reprocessing and its value and its consequences, etc., are still open for discussion. And that you will get probably one party agreeing that reprocessing is sensible and others significantly arguing it is not. Why reprocessors, as we've said in a few minutes ago, it's again conservation of natural resources. If we can use the recycled and recovered uranium and the plutonium, then obviously the argument would be we will need to mine less uranium out of the ground, as we talked about earlier in the week. Reasonable argument, always open to or for discussion. And currently we have about 420 reactors operational throughout the world. There's about 60 under construction, and there is prediction of a further 250 reactors will be constructed by 2040. Bear in mind, ladies and gentlemen, equally there'll be a couple hundred reactors will be coming offline because they've reached the end of their life expectancy. So that 400 may stay roughly round about a constant number for this, for certainly the next 5 or 6 decades. Again, optimization of waste management, highly debatable. Minimization of environmental impact, highly debatable. Improved fuel cycle economics, very debatable. Proliferation resistance, equally debatable. So although when we were reprocessing, we could use some very strong arguments, there are equally strong arguments against reprocessing. And you will see from the numbers in this overhead, ladies and gentlemen, the majority of spent nuclear fuel is not reprocessed. As it says there, something like 100,000 tonnes, probably 120,000 tonnes, out of a total greater than 320,000 tonnes, so less than a third of spent nuclear fuel has been reprocessed. Where's the other 220,000 tonnes, which we will discuss in the second presentation? And now, as a result of, excuse me, as a result of the closure of Thorpe in 2018 and the prospects, or certainly not the prospects, but the closure of the Magnox reprocessing plant later this year, if it hasn't already closed, then the world reprocessing capacity is now down to 3,000 tonnes per year. And bear in mind, we've got something like 420 reactors. Each of those reactors will discharge, on average, about 25 tonnes a year of spent fuel. Roughly 25, 30 tonnes a year, depending upon the type of reactor, of course, and its burn-up, etc. So there is considerably less capacity in the future than what we've had in the past few decades because of the UK stopping reprocessing. Okay? Between now, as it says there, and 2030, another 400,000 tonnes of used fuel is expected to be generated worldwide. Now, obviously, some of you who are a bit quick at mathematics will probably sit down, or I've sat down there and said, but hang on a minute, Harry, you said that only 25 tonnes a year comes out of a reactor. So why is it 400,000 tonnes? And it's quite simply, ladies and gentlemen, it's because of the number of reactors that are coming offline by 2030, and some of those reactors will have the best part of a few hundred tonnes of spent fuel in them. This is why that number is so large. So what are we going to do with this extra, for want of a better word, inventory of spent fuel? Hopefully, we'll be able to explain that in the second presentation. I emphasize hopefully. These are the these are the reprocessing plants, beg your pardon, that's been operated around the world, as you can see, France, UK, Russia and Japan. I'll pick up on Japan in a few minutes. We've been the principal reprocessors for light water reactor fuel. Japanese at a capacity of 800 tonnes heavy metal, what we normally talk about in the industry, heavy metal throughput a year. That particular plant as yet has not operated. Fukushima had a major impact on its operation because of the Japanese government and the reactor and the nuclear industry operators in Japan were a little bit, to say the least, concerned. It should have operated 3 or 4 years ago, long before Fukushima incident, in fact. It's now delayed to possibly, and I emphasize possibly, 2024. If you recall what we argued earlier, we said, well, reprocessing is economically sensible. That Japanese reprocessing plant, according to some observers, has increased in value or costs tenfold. The Chinese were thinking of building another reprocessing plant bigger than the small scale plants they have, and they found that the cost of doing so, based on a French design, was unacceptable. They may still come on to the reprocessing field, but at the moment, not so. In addition to light water reactor fuel, excuse me, as we've said at Sellafield, we've reprocessed Magnox fuel, and in fact, the Magnox reprocessing plant has reprocessed more fuel than any other reprocessing plant in the world, and has reprocessed more fuel than whole of the other reprocessing plants in the world. It's a very, very, if you like, flag in the UK nuclear industry's achievements. Unfortunately, these days it's not seen as such. But such is the technology that was developed way back in the 1950s for the successful operation of the Sellafield Magnox reprocessing plant. India's got 4 plants, but as you can see, 330 tonnes. Without being discourteous to our Indian colleagues, probably more of a demonstration than a commercial operation. And then again, it shows you at the bottom there that Thorpe's closed, Magnox will close. We're not quite sure when the Japanese reprocessing plant will operate. We've seen from a previous slide that the bulk of these spent fuel hasn't been reprocessed. So what are the options, which we'll pick up again later in lecture 2? What are the options for spent fuel, irradiated fuel? Well, we can go once through with direct disposal. I'll come back to that in a minute. Postpone the decision with storage, or we can recycle post-treatment, i.e. reprocessing. And we've just agreed that only a third, or even less than a third in the future, of spent fuel will be reprocessed. So are we therefore thinking of once through with direct disposal? No. No one as yet has used that particular option. The second one, postpone decision with storage, is by far the most popular decision and has been for many years, full stop. Hence why we've got something like nearly 250,000 tonnes of spent fuel in storage. And that's the option we will be discussing later this morning. So very quickly looking at the differences in the fuel, certainly in the United Kingdom, and I'll stick with the United Kingdom for most of the lectures now. Magnox, and this has given you some indication of the difference between Magnox fuel and oxide fuel, whether it be AGR or PWR fuel. That's probably associated more with AGR fuel than PWR fuel. And it hopefully, when you look at these numbers, it may give you some indication of why the Magnox reprocessing plant is different to Thorpe. And one of the, or some of the reasons are the burn-up, and it defines what burn-up we mean by burn-up. In Magnox, around about 5 gigawatt days per tonne. In oxide, 40, 8 times. And that tells you something about the amount of radioactivity of that spent fuel, of the oxide fuel. Uranium, 994. Hang on, Celia will let you in a minute, or Javad will, or somebody will, right? 994, not a significant difference between Magnox and oxide fuel. Plutonium isotopes, 3 kilograms per tonne. So in other words, 940 kilograms of uranium would be associated with roughly about 3 kilograms of plutonium. Now compare oxide. We'll not worry too much about the plutonium because it's not a significant difference. But the plutonium is 3 times or more higher than in Magnox fuel. Neptunium isotopes are significantly higher, and look at the total fission products, again 10 times or more higher than what you would see in Magnox. That infers that the reprocessing plant and its operation is going to be totally different for Magnox as opposed to AGR fuel or PWR fuel. And on the photograph on the left is the first generation reprocessing plant. That's, I think, if I remember right, it could be 204. And on the right hand side, that's Thorpe, and it's by far, in terms of footprint area on the Sellafield site, far greater than the 204 and 205, which was Magnox reprocessing, by far significantly greater in footprint area. So what happens when we take the fuel out of a reactor? It's done its duty, it's generated all the electricity, it's produced some plutonium, it's produced some fission products, it's produced the actual fuel is highly radioactive. It comes out of the reactor, and probably for the first 100 to 200 days on the reactor site, it will be stored underwater in their reactor ponds, fuel ponds, okay? If we're talking about Magnox, after about 180 days, it will be taken out of the ponds, it will be placed into an overpack. I'll use the word overpack. This overpack is constructed of very thick lead, because bear in mind we're now dealing with a highly radioactive material. It would then be transported to Sellafield for reprocessing. Light water fuel, AGR fuel, probably, more than probably, will spend a little longer in the actual reactor ponds to allow the short-lived fission products to decay. That's equally true for the Magnox. But remember the slide we saw before, excuse me, in comparison to Magnox fuel, the amount of fission products in the light water and AGR fuel is 10 or more times greater. Hence, the actual decay heat associated with the light water and AGR fuel is significantly greater. So therefore it will need a longer period of storage in the ponds at the reactors before being transferred to Sellafield for reprocessing. And when it arrives at Sellafield, the Magnox fuel used to spend something like 100 and 200 days further underwater storage as opposed to the 180, 200 days at the reactor site. Equally with light water and AGR fuel. It will be stored underwater again to allow short, medium-term radioactivity from short, medium-term lived fission products to decay away. Okay. Once it's been stored underwater, we then retrieve it, and bear in mind, whether it's Magnox, it's got this outer casing of the Magnox alloy that we can see there, yeah, or it is encased in a stainless steel if it's AGR fuel, or zircaloy pin if it is light water reactor fuel. And the first thing we have to do is, certainly for for Magnox fuel, we have to remove that Magnox can. And we can do this simply. We can do this mechanically. We actually push the rod, and bear in mind we're talking about a uranium rod of about a meter length, something like, let me have a quick look, about 5-6 centimeters in diameter, and it's fairly close fitting, or will be close fitting to that Magnox can. So we shove it through a die, as you can see there. We extruding that can away from the uranium rod. Okay, very simple. That die will have probably the same size as the uranium rod itself. So therefore there'll be very little of the Magnox can remaining on that rod. And that the debris of that Magnox can, that's intermediate level waste, which we'll talk about this afternoon. For AGR and light water reactor fuel, that's in terms of preparing it for dissolution is different. Both the rod and the pellets are going to be dissolved in nitric acid. Fortunately, stainless steel and zircaloy are fairly resistant to nitric acid, 7 molar nitric acid. Whereas obviously Magnox, it would effervesce, it will create a lot of gaseous byproducts, and that's why we remove it from the actual rod. But with AGR and PWR fuel, we simply chop the rod or chop the outer casing. We chop it into something like 5-6 centimeter lengths. Bear in mind, the AGR fuel is still inside, and we chop it into these lengths because we can immerse that fuel with the outer casing still intact. We can immerse it in the dissolver because stainless steel and zircaloy do not react do not react quickly with nitric acid. Full stop. What's the next process? We've now got the uranium rod or the uranium oxide pellet now dissolved in nitric acid. We'll come on to that in a little minute, but the next process is obviously we want to recover the uranium and plutonium. And this is why in the outset of the of Monday we talked about liquid extraction. Okay, so I'm not going to spend a great deal of time on liquid extraction because we've already been there, and you're now all professional in liquid extraction. That's some terminology of what solvent extraction, if you like, name dropping is, what we mean by the extraction, solvent, etc. That's fairly straightforward. So again, I'll not spend any time talking about that. Have a look at it, and again, it will then improve your professionalism as being a liquid extractor. I'll stop in a few minutes, ladies and gentlemen. Criteria for selection of solvent systems. Obviously, there are some very sensible reasons why we pick TBP and also odorless kerosene for the solvent phase. And for Magnox, the concentration of TBP in the odorless kerosene is 20% volume, but for AGR and light water reactor fuel, it is 30%. But that tells you why we've selected that particular type of solvent system. Okay, very quick. We'll just cover this one and then we'll break. Remember what we talked about on Monday, contactors, not contractors, contactors. And this is the mixer settlers we described. Here we've got the mixer, here we've got the settler. Here we're talking about a pulse column, and this is the internal parts of the pulse column. And this is the centrifugal contactors. A good number of overseas reprocessors have tried these out. Not necessarily at a commercial scale, but certainly demonstration scale. And in all of these processes, if you remember, it is a counter-current operation. The actual solvent will be flowing one way, and the aqueous phase, the uranyl nitrate in nitric acid, will be flowing in the opposite way. Okay? And I'm sure you all remember that as from Monday. Right, we'll stop there and have 5-6 minute break. Is that okay? Are there any questions? Anybody?
Harry, there was a couple of questions.
Are people still out there? Or have I been talking just to you, Javad?
No, you've been doing very well. There were two questions. I would ask the gentleman to repeat it to you.
Right, let's have 5 minutes then.
Bear with me a second to stop the recording first.
Yeah. I might overrun in the next session, Javad. So
yes, you're running.
forgive me if I do so.
Sorry, what